Stanford University.
Okay, let's go on. In fact, let's forget for the moment the spin system. We'll come back to it for sure. Probably tonight. In fact, definitely tonight. But let's remind ourselves of, I think I wrote down 4 principles of quantum mechanics last time, and I want to write them down again, and then move on to a 5th principle. In fact, they're not all independent. It's easier for me to explain them one at a time than to try to derive from the minimal, absolute minimal number of them. And I don't think there's any particular advantage in doing that, so we'll just write down all the principles that I wrote down. The first one is that observables are the things that you measure. They could be called measurables, and if it was up to me, I would have called them measurables, but they were called observables. Observables are represented, and I'll just use the equal sign to indicate that. Observables are represented by Hermitian operators. I'll use the symbol L for the moment for Hermitian operator. Not all operators, not all linear operators are Hermitian, and it will not always be the case that the symbol L will stand for a Hermitian operator. But right now, L stands for a Hermitian operator, any Hermitian operator. Every observable is identified with a Hermitian operator. Now, the question of whether every Hermitian operator is a thing which can be measured is a generally hard question. You have to, what can and can't be measured depends on what kind of materials you have available, all kinds of things. Generally, the abstract rule or the folk rule, let's call it, is that any Hermitian operator is identified with an observable, and someday somebody will figure out how to measure it. Okay, but the other way, that any observable is identified with a Hermitian operator, that's for sure. The eigenvalues of a Hermitian operator, let's call them lambdas. Lambda is the eigenvalue of L. The eigenvalues represent the possible numerical values that L can exhibit when it's measured. Okay, so eigenvalues of L, which equal lambda. No. They represent the possible observed or the possible outcome of experiment. Possible outcome of an experiment to measure L, of L measurement. Okay, I think we had a third one along the line here. Yeah, physically distinguishable states. Now let's just see what physically distinguishable states mean. Certainly up and down are physically distinguishable. And the meaning of saying 2 states are physically distinguishable is that there exists a measurement of some kind that you can do that can tell you the difference between an up state and a down state. In other words, somebody hands you a spin from out of their pocket, and they say, I created this spin, I prepared it in a state which is either up or down. Can you do an experiment to unambiguously tell me which one it is? Yes, you tilt your apparatus until it's pointing along the z-axis and you make the measurement. If the state was up, you will get +1. If the state is down, you will get -1. No ambiguity. The same is true for left and right. Different measurement, different thing that you would measure. You would measure the x component and you would tilt your apparatus along the x-axis, but same deal. On the other hand, supposing somebody, that same person, came along and said, here, I'm going to give you a spin, here it is, and that spin I either prepared up or I prepared it right. I am not going to tell you which way I prepared it. I'm not going to tell you which way I tilted my apparatus when I did the preparation. I'm just going to tell you it's either it's either up or right. Can you do an experiment which will uniquely tell you the difference? The answer is no. For example, supposing you decide to measure the spin along the z-axis. Well, if it's up, you'll get +1. If it's right, with 50% probability, you'll get +1. So you can't be sure whether you were up or right.
What do you get if you oriented at 45 degrees?
Still, you would have a probability for, yeah. It would not be unambiguous. Right, okay? So the next postulate.
Excuse me, in your last statement, that's assuming that it was prepared along the z-axis. If it had been prepared along the x-axis, then if you measured the x-axis first, you get that it was.
If you measure the x-axis first, you'll find something out, but you could have found out exactly the same answer if it was along the z-axis. In either case, there is some probability of getting the same answer whether it was up or right. There's no experiment you can do which unambiguously will determine which it was. All right, so that leads to the notion, I'm not going to try to give a more precise definition of it. That leads to the notion of physically distinguishable states, by which is meant that there exists an experiment or a set of experiments that can unambiguously determine which of the two states you're talking about. The next postulate is that physically distinct or physically distinguishable states are represented by orthogonal vectors. Okay, so physically distinct distinguishable, same thing. A little easier to write distinct. Physically distinct states imply orthogonality. All right, I said that observables are Hermitian operators. I could have just said linear operators. Let's leave it at linear operators for the moment. But let's add a postulate that the result of every experiment, every simple primitive experiment, is a real number. If it's a real number, if it's a complex number, it really means that two independent things were measured. The actual results that come out of your apparatus, that come out of your, the needles on your apparatus, they're real numbers. So I'll add that as a postulate. The results of experiments are always real numbers, and therefore the eigenvalues of observables are real numbers. Now that does not prove that the operators are Hermitian. Not enough. Not enough. The other added thing is that the various eigenvectors with different eigenvalues, physically distinguishable states, are orthogonal. Okay, that's this third postulate, and that tells you that observables are Hermitian operators. It's the Hermitian operators whose eigenvalues are always real and whose eigenvectors are orthogonal. That's necessary and sufficient. So this one, as I said, they're not all completely independent of each other. One, 2, 3, and let's write number 4 now. I forgot what 4 is. Oh. Well, yeah, what was 4? Yeah. The probability principle. Okay. The probability principle, it's also called Born's rule. Max Born. Born's rule, let's just call it Born rule. But it's a rule for probabilities. So far, none of this has much content. The added content, well, no, it has content, but the real bite here is for the prediction of probabilities for various experiments. And the Born rule is the rule for how to calculate probabilities. The Born rule says, if your system has been prepared in state A, all right, system in A, and you measure L, the observable L. Now I'm using interchangeably the physical idea of the observable with the operator which represents it. I'm not going to make a special language where the operator will always be called the operator and the observable L, same, they come in pairs. All right, so if the system has been prepared in state A and you measure L, the outcome is going to be one of the eigenvalues. So the only question you can ask is, what is the probability that you get the answer lambda? Okay, one of the specific eigenvalues. The answer is the probability that you get result lambda, that's the probability that you get out of the various eigenvalues that you get lambda, is equal to the square of the inner product of the state vector that the system was in with the eigenvector corresponding to normalized eigenvector. All vectors are normalized now. The inner product of A with lambda squared. A with lambda, the inner product, sometimes incidentally the inner product is called the overlap. It's a measure, if we said that orthogonality is complete distinguishability, unique and complete distinguishability, then a lack of orthogonality represents to some extent the inability to make the clear distinction between two states. Yeah, all right, so this is, yeah, question.
I'm surprised to see lambda represented as a vector because it's a value.
No. All right, the notation is every eigenvalue is associated with an eigenvector. I'll just write E vector. And the notation is that the vector labeled by lambda is the eigenvector associated with the eigenvalue lambda. That's a good point. I mean, that the problem with trying to be a purist about notations is that notations get very complicated. And they get so complicated that they're difficult to read. There are too many indices. There's too many different letters you have to use. So, yeah, sometimes we use a slightly, excuse the word, bastardized notation where we conflate a symbol for a vector with a symbol, in this case, for an eigenvalue. Good. Okay. Yes, that's the probability principle, or Born's rule. And let's just look at it for a minute. You might say, why the square of the absolute value? Well, in general, these overlaps are neither positive, not even real in general. Overlaps between two vectors are not necessarily real. In fact, in general, they're not. We're talking about a complex vector space, and if the components of the vectors are complex, and generally the inner product will not even be real, let alone positive. Okay? On the other hand, the square of the, or the absolute value of the square of the absolute value of the inner product, that is real. It's not only real, it's also positive. Okay? So this has a chance to be a candidate for probability, whereas the inner product itself doesn't. The inner product itself is called a probability amplitude. So a probability amplitude is a thing that you square in the sense of absolute value to compute a probability. Needless to say, the justification for these principles in the end is experiment. On the other hand, you could ask, how much can I bend them and still make physical sense out of the predictions? The answer is nobody has ever found a way to change the rules of quantum mechanics and still preserve a reasonably logical structure. So you'll eventually get familiar with these principles. Yeah.
Which of these principles took you from several possible outcomes to one actual outcome?
Well, okay. If A is an eigenvector of L, if it is, if the starting state of the system happens to be an eigenvector of L, then it will only have an inner product with one of the eigenvectors. Right. So that's, again, these are good questions.
If you say L ket lambda equals lambda ket lambda, it kind of shows
Yeah.
you.
Yeah. That's right.
Excuse me, what if lambda is an eigenvalue for multiple eigenvectors, all orthogonal?
Yeah, still, the rule is the same, but what you, right, okay, I'll give you two answers. The first answer is, don't worry about the case where the eigenvalues may be the same, because it's very special, but that's not good enough. Let me say what the right answer is. The right answer is if you want the probability for a given value of lambda and there's more than one eigenvector with the same value of lambda, then you add them. You simply add the sums of the squares of the just probability addition. So the questions tonight are really good. Yeah.
And what about the case where A has overlap with several different lambdas?
Yeah. Then you take the sums of the squares of them. You take the sums of the square. If there are several different eigenvectors, all with the same eigenvalue, first of all, you make them perpendicular to each other. You can always make them perpendicular to each other.
Different eigenvalues.
No, even if they were the same eigenvalue, there's the theorem. Okay, let's go back to the theorem. The theorem says that the eigenvectors with different eigenvalues are orthogonal. It doesn't tell you anything about the eigenvectors for the same eigenvalue. All right, so supposing you have two eigenvectors with the same eigenvalue, then it's also true that any linear combination of those two eigenvectors is also an eigenvector with the same eigenvalue. For example, let's suppose lambda 1 and lambda 2. Now, these are not two different values of lambda. These are the same value of lambda, but two different eigenvectors. Maybe we should write it like this. Lambda 1 and lambda 2. Two different eigenvectors, both exhibiting the same eigenvalue. Then you can take any, what that means is that L on lambda 1 equals lambda times lambda 1. L on lambda 2 equals lambda 2. Multiply this by any complex number alpha. This one by any complex number beta. And add the two equations. What you find is that L on the linear combination, the linear sum, alpha lambda 1 plus beta lambda 2 is equal, on this side now, you have lambda times the same thing as in the bracket here. In other words, if you have two eigenvectors with the same eigenvalue, you can add them with arbitrary coefficients, and they remain eigenvectors. Now, given two distinct vectors, and all the possible linear combinations of them, you can always find perpendicular combinations. You got this one, you got this one. Now we can always add them or subtract them with coefficients to make them perpendicular. So the rest of the theorem is that if the two eigenvalues are the same, you have the freedom to choose two eigenvectors which are perpendicular, which are orthogonal. All right, and the end of the day, to summarize the theorem, is that given a Hermitian operator its eigenvectors can be chosen so that they form a basis, so that they're orthonormal, perpendicular to each other, and normalized. Okay, so where were we? That was an interruption, but I don't remember where I was. That's the problem with interruptions.
We just finished Bourne's rule. You were just talking about Bourne's rule.
Yes, I was talking about Bourne's rule. Right. Oh, good. Okay. So now, if you happen to have several eigenvectors, let's say lambda 1 and lambda 2, both with the same eigenvalue, then you construct the overlap of the state vector with lambda 1. You construct the overlap of the state vector with lambda 2. You square this one, you square this one, and you add them. In other words, you simply add the probabilities for the two possible ways that you could get the same lambda. Just the sum of probabilities. Thank you, Sanjay. You're already too late. I already got Oreos. But my wife would say, this is probably healthier than Oreos. Yeah, it is. What? Yeah, you eat the Oreos?
You want to hurt their feelings?
Yeah. Excuse me. Okay. Yeah. Go ahead. Loud and clear.
Could we say also that the reason why those things are squared, regardless of whether they're complex or not, is so that the total probability adds to 1, right?
Yes. Right. We know it's the sums of the squares of these things which add up to 1 for normalized states, for normalized vectors. That's right. I'm not sure which one implies which, but clearly they fit together very nicely. Good. Okay.
Question. Is it possible to get an unambiguous result from an unprepared experiment?
I'm not sure what an unprepared experiment means, but I think what you're asking is, supposing somebody gives you a spin and they don't tell you anything about how they prepared it. They just said, here it is, I give it to you, I tell you nothing. Then it is not possible to find an experiment which has an unambiguous answer. Right. Another good point. Okay, now we need to come to a new idea and a new question. In classical mechanics, all of this whole story here was summarized when I showed you a heads and a tails, and I said those are the two possible states of a simple system. We didn't talk about measuring it. It was all sort of obvious, and we didn't have to, because we know that measuring doesn't do very much to a system. You measure, but that doesn't change the system in any way. Here we come to a much more complicated story, but the story up till now is really the quantum mechanical analog of just specifying that you have a collection of states. The next question we asked was, how do states change with time? That we called, in the classical case, dynamical laws of motion, or dynamical laws of nature, or whatever, the rule for how a state changes. If you remember, there were some examples. The coin, a simple example would be, put the coin down and the rule is nothing happens. It just stays the same way. Well, that's pretty trivial. Another possible law is, in each interval of time, and we have a stroboscopic time that we can imagine, and in each interval of time, it flips. Up, heads, tails, heads, tails, heads, tails. That's a perfectly good law. We talked about the same concept in the context of a die with 6 faces, or any number of faces, including continuous infinity. Same basic idea. The laws of physics are an updating from instant to instant of a configuration. And they tell you how the configuration changes. And if you have good laws in classical physics, they're deterministic. They tell you how the state changes. But also another rule, and the other rule we called reversibility. Reversibility was basically just the idea that states don't run into each other, that states which are distinguishable, namely different, heads and tails are distinguishable, two states which are different will evolve mathematically and stay different. All right, that was the idea of reversibility. And what it comes down to is exactly that, that if you know the state at any instant, you not only will know what comes next, but you will also know what came before, because there's no chance that states run together and two different states giving you the same outcome. Then you wouldn't be able to tell where you came from. So reversibility is the idea. We also called it information conservation. And I suspect I referred to it as the minus first law. Minus first because it comes before everything else. Quantum mechanics also has a rule of both reversibility and information conservation. You can call it the minus first law, but it comes down to the same thing. States which are distinguishable, in the sense that I said, that there exists an experiment that uniquely distinguishes them, stay distinguishable. All right, so now we want to talk about how states evolve with time. We're going to come back and discuss this in the context of the spin. It's the simplest system of quantum mechanics, and it's a good idea to get it all down for that. But let's talk about it more generally. Okay, here's the postulate. The postulate is that if you have a system at some specific time, let's call it a time zero. And I'm going to start changing my notation for states. Instead of calling them A and B, I'm going to start using a notation which is more or less the standard notation in quantum mechanics. Call them psi. Psi is a Greek letter. And psi is a commonly used letter to represent the state of a system. Now, the states of systems do change with time. So you have to think of these vectors as being functions of time. They evolve. So let's put that in here in the following way. Psi of t, this simply represents a state which changes with time. Which state? Could be any state. It's not the same after a certain time as it was to begin with, but we're following one specific state of a system that's been prepared and then allowed to evolve by whatever means things evolve. All right, the postulate is that psi of t can be obtained from psi of 0, this means time 0, by an operation on psi of 0, a unique, definite operation which is governed by the laws, by the quantum mechanical laws for that system. So we have to do something to the vector. It doesn't stay the same. So let's represent what we do by the operation of some kind of operator. Now, incidentally, we didn't have to start with time 0. We could have started with time something else and evolved by amount t. So this t here really represents the time of evolution from the initial state to the final state. Well, not necessarily final, but the state at some time. The basic postulate, two basic postulates. The first is that U is a linear operator. That U is a linear operator, and the same U for any state. Whatever the initial state is, you put that here, and you hit it with the same U, the same operator. In other words, this is called the time development operator. It's a linear operator, and it evolves the state from one instant to another. You could try to ask what would happen if you made a more general hypothesis. For example, you might have the hypothesis that U depends on the initial state. Or you might have the hypothesis that U is an operation but not a linear operator, some other kind of operation. You can try it. You'll very shortly run into big troubles with all kinds of things. It's been tried, I guarantee you. It's been tried, and repeatedly, every so often, some physicist will try to invent something, and then some other person will come along and say, look, that has troubles with locality, or it has troubles with causality, or it has troubles with probability interpretation, and you're free to try. I've given up trying. I actually never tried. Right, okay, so U is a linear operator with all the rules for linear operators, but one other thing, and that's this idea of conservation of information or conservation of distinguishability, that if you have two states, two different states of the same system, and you evolve them, let's call phi of t, phi, capital Phi, that's given by the same U of t, the same operator, times phi at time 0. Then, if phi, to begin with, is orthogonal to psi, in other words, if they're physically distinguishable to begin with, then they will remain orthogonal for all time. Yes.
Is there anything to the fact that you used uppercase letters on the left and lowercase?
Say it again?
The Greek letters are uppercase on the left and lowercase on the right. Is that just?
It's because I'm sloppy. Right. No. Right. All right, so orthogonality breeds orthogonality. Physically distinct states evolve to physically distinct states. Distinguishability remains intact. It's the immediate analog of the minus first law of classical mechanics. So let's see if we can find out what it says. Oh, incidentally, it's very easy to prove from that. Well, what does it say? It says that if psi and phi were initially orthogonal, all right. No. If they're initially orthogonal, then don't ask me to make capital letters. It's much quicker to make the lowercase ones, but I mean capital here. I mean uppercase. Then this is true, and it remains true for all time. It's an easy exercise. I will leave it to you to prove that if orthogonality is preserved, that you can say a stronger thing. It's implied by this. You can say if you take any two vectors, which may or may not be orthogonal, the inner product between them stays constant with time. There's a nice little trick. You take any two vectors, you expand them in basis vectors, and then you assume that the basis vectors remain orthogonal with time. Then you can prove that the inner products of any two vectors is time independent. Right? So it follows from the orthogonality, the evolution of orthogonality, that the inner product between two states remains the same. The overlap between them remains the same. There's a sense in which the overlap between two states is of course, a measure of their similarity, and what it says is the degree of similarity remains the same. Okay, let's see if we can figure out what that means for U. What it says, let's rewrite this by plugging in for phi of t and psi of t, the product U times phi and U times psi. But before we do, we have to remember that we have to flip this equation. Whoops. Chocolate bar. Is this chocolate? Yeah, it is chocolate. We have to flip it from a ket vector to a bra vector equation. Okay, so let's do so. This is psi of t equals psi of 0, not times u, but times what? U dagger, the Hermitian conjugate. Not the it's related to the complex conjugate, but the Hermitian conjugate. All right, so now we plug this into this equation here. And what it says, let's write it out. Do a little bit of erasure. For arbitraries, they don't have to be orthogonal. Whatever they are, they have some inner product. That's equal to psi of 0, u dagger of t, u of t, phi of 0. All I've done is plug in. For phi, u of t. For psi, u dagger of t. Now, the product u dagger times u is another operator. What is the product of two operators? We didn't talk about this, but the product of two operators is a very simple concept. You take a linear operator and you apply it to a vector, and then you take the result and you apply another operator to it. The process of repeatedly applying two operators gives you an operation which is called the product of the two operators. So that's what this is. First you hit phi with u, and then you hit the result with u dagger. And what this says is that for any phi and psi at all, that when you plug in here u dagger and u, the product of u dagger and u, you get something which is exactly the same as had you not evolved the state. The inner product stays the same. Whoops, I think I made a mistake. One of these should be phi, right? All right, so that's the principle of conservation of overlap, if you like. Well, here's a theorem. We don't need to. This is, again, very, very easily proved by going to a basis, very easily proved, that if the matrix elements, this is called the matrix elements, or the product like this, if this equation is true for any pair of vectors, in other words, I'll write the theorem in general. If you have an operator, let's call it k for u dagger u, and for any pair of vectors, psi k phi is equal to psi phi, for any pair of vectors, whatever, it follows that k is the unit operator. The unit operator is the operator which does nothing, just gives you back the same vector. So it follows then that u dagger times u must be the unit operator. That's the content of conservation of overlap. U dagger of t for any t times u of t is equal to the unit operator, meaning the operator which does nothing, just gives you back the same vector.
Question? Can you then say that one is the inverse of the other in matrix algebra?
Yes, you can.
Okay.
Yes, you can. Indeed. All right. Let's examine this a little bit now. In particular, let's examine it for very, very small time. For very small time, in other words, where you only evolve the system by a tiny little incremental time, let's call the incremental time epsilon. All right? Now let's write that u of epsilon, now first of all, what is u of 0? No time evolution at all. Just one, just a unit operator. So for very small epsilon, u must be itself close to the unit operator, plus a small deviation, presumably of order epsilon, and that will be right. It will be of order epsilon. So there will be something of order epsilon times another operator here. I'm going to make use of freedom and that I have, and I'm going to put a minus sign here. We're going to put an operator over here. This minus sign has no content yet. Unless I know what the operator is over here, the minus sign, it just absorbs into the definition. And I'm also going to put an I here. Right? Again, there's no content yet because I haven't told you anything about H. H is some operator. Epsilon times H is just an operator, and I epsilon H is just an operator. So I have not really said anything other than for small epsilon, the operator U is close to the identity. How close? Of order epsilon. And then there may be additional things of order epsilon squared, epsilon cubed, but we're going to drop them and study this equation. Oh, we should give a name to this equation here. More specifically, we should give a name to operators which satisfy this rule. U dagger times U is equal to 1, or, as was said, that U dagger, the Hermitian conjugate of U, is the inverse of U. Such operators are called unitary. U is a unitary operator. So this is, again, this is a restatement of the principle of conservation of overlap. Let's now apply this equation, this condition, to U of epsilon and see what we find out about H. Okay, so let's bring it over to this blackboard. U of epsilon is equal to 1 minus I epsilon H. Now let's do it over here. All right. What about U dagger? U dagger is the Hermitian conjugate. The Hermitian conjugate of 1 is just 1, but then we have the complex conjugate plus I epsilon, and then we have to Hermitian conjugate H. Okay? All right, so here is U dagger and here is U. And now let's multiply them together and set the result equal to 1 to order epsilon. To order epsilon. Okay, so what do we have? We have U dagger is 1 plus I epsilon times H dagger times 1 minus I epsilon H. That has to equal 1. And now just expand it out to order epsilon 1 plus I epsilon H dagger minus H equals 1. As I said, that's just to the approximation that epsilon is so small that its square can be completely ignored compared to order epsilon. All right, so the ones cancel. And basically what we find is that H dagger minus H has to be 0. We canceled out the ones, we get 0 on the right-hand side. And so to order epsilon, H has to equal H dagger. This is the condition that H be Hermitian. Okay. Now I didn't call it H for Hermitian. I called it H for something else. I called it H for Hamiltonian. Okay, what it has to do with the Hamiltonian of classical mechanics will eventually become clear. Right? The Hamiltonian for classical mechanics also enters in to the equations for how systems evolve from one instant to the next. But of course, that's not a good enough reason to call this the Hamiltonian. We want to see that it enters the equations in a way very, very similar to the way the Hamiltonian enters into classical mechanics, and it does. It is also the thing which, it's Hermitian, right? That means that it's an observable, or it could be an observable. It's a Hermitian operator. It could be an observable, and it is an observable. It's the Hamiltonian, it's the energy. Hamiltonian and energy are the same. This is what the energy of a system is. It's the Hamiltonian which generates the evolution of state vectors according to this rule here. Yeah? It could be any Hermitian operator at the moment. Now, what determines what Hermitian operator you put there? Well, it can't be, yes, it can be any Hermitian operator associated with the system you're studying. If we're studying a system of one spin, we want to make it up out of operators that are associated with the spin. So yes, it can be any operator, but it's either experiment or some, it's the same things which govern why you choose one Hamiltonian or Lagrangian in classical mechanics. Either experiment, some prejudice about the way things work, some symmetry principle, whatever you have that might give you a clue as to what H is. At the end of the day, you may have to resort to experiment to find out, but whatever it is. Okay, so that's right. So now let's rewrite our equation. Let's rewrite. Question? Yeah.
So when you do that expansion like that, normally then H is a constant, right? That's what you normally mean when you do that first order expansion.
Mm-hmm.
So it'd be, it's the H of
Well,
zero.
H is an operator.
I mean, it's not a function of time when, in that case, right?
Okay.
Or not a function of epsilon.
The situation with a possible explicit time dependence of H is the same as in classical physics. In classical physics, H can depend on time. For example, if you have a particle moving in a magnetic field and the strength of the magnets is being varied with time by changing the current through the electromagnet, then the Hamiltonian for the particle moving in a magnetic field is time dependent. Okay? Otherwise, if the parameters of the problem are not varying with time, then you say the Hamiltonian is not time dependent. It's exactly the same.
You don't really do an expansion like that. You'd be using, say, H of zero.
Yeah, no, that's right. That's right. In principle, H could be a function of time. Let's take the case where it's not, and what that corresponds to is the situation where the parameters of the problem are not time dependent. Where in classical physics we called it time translation invariance. Okay, remember in classical physics, time translation invariance, which means like every time is the same as every other time. Okay? You do the experiment, the same experiment at a later time will have the same output as the identical experiment at an earlier time. The statement of that principle, time translation invariance, is that H does not have explicit dependence on time. It's just an operator which doesn't depend on time. As I said, you can imagine situations where you're ramping up the current in an electromagnet, or the universe is expanding, or God knows what, there's some explicit time dependence, then H can be time dependent. Now, do you remember what happens to energy conservation if the Hamiltonian is time dependent? Down the drain, right. Same thing here. If the Hamiltonian is time dependent, and we haven't yet seen why there might be a conservation of energy. We'll come to that, but all right. Okay, so let's come back then to this equation over here.
What happens at the long time?
What happens to what?
This is all for the small epsilon time.
Sorry, what? Say it again?
This is for the small, infinitesimal small.
Yes. Yeah, we'll come to that. Basically, you just multiply them together. Right, we'll come to that. Okay. Or you can think of it another way. After you've updated by a small amount of time, you just do it again and again and again. All right? You just do it repeatedly. But we can use this to derive a differential equation for the way the state changes with time. Let's do that. Let's do that. Okay, so let's look at the state of the system at a time epsilon. And this time epsilon could be thought of as a time epsilon right after some arbitrary time, which I'm going to call 0, but it doesn't matter. So I have epsilon is equal to 1 minus I h epsilon minus IH epsilon times psi, let's say at time 0. Or another way to say it is that psi of epsilon minus psi of 0, this is the small incremental change in the state vector, that's equal to minus I epsilon operation by H on psi. Now, as I said, this 0 here doesn't have to be 0. It could be any time as long as epsilon is epsilon units after the starting time. Okay, let's divide this equation by epsilon. You're allowed to do this because you can multiply vectors by numbers. So we're just multiplying both sides by 1 over epsilon. 1 over epsilon times this whole thing. Okay, what's this thing on the left-hand side? 1 over epsilon times the difference of two things which at two slightly different times. That's just the time derivative of this vector. We haven't talked very much about taking derivatives of vectors, but it's clear you can do that. You can take the difference between two vectors, that's perfectly well defined. They will be close to each other if epsilon is small. If you divide by the small epsilon, you'll get something which on the right-hand side is just the time derivative of psi. The time derivative of psi equals minus I h psi. At any given time, it doesn't, as I said, it doesn't have to be at time 0. At any given time, if you want to find out how the state of the system changes over an incremental time interval, this is your equation. Completely analogous to the way you update classical systems, but because knowing the state vector is not the same as knowing the values of the experimental outputs of experiments. You can know the state, and still there can be ambiguity or uncertainty in the value of an experiment. This tells you how states change, but it doesn't tell you how the results of experiment change. The results of experiments are still statistical, but with a continuously updated state vector. Okay, this equation has a name. The name of this equation is the generalized time-dependent Schrodinger equation. This is the general form. This is the Schrodinger equation. Specific versions, what Schrodinger wrote down was a very specific version of this. We're going to come to that later in the course, but this is the general idea. The rate of, all right, I don't need to say it again. This is what it is, but of course, in order to use it, you have to know what h is.
Question?
Yeah.
So all of this is dependent on the reversibility of the system, is that right?
Yes.
So, I guess...
Or the conservation of inner products, yeah.
Right, so I guess stepping back, how does that match with the fact that if you take an up vector and a down vector, and you measure them along the horizontal axis, they can sort of both end up, in sort of what I guess what would seem to be indestructible states.
That's a good question. You have to remember, when you do that, you're intervening with an apparatus. In order to follow the system, under those circumstances, you have to include the apparatus as part of the system. You cannot interact with the system and not include the things which are interacting with it in the system. Classically, it's not such a bad sin. But quantum mechanically, if something interacts with the system strongly enough to affect it, or strongly enough to measure it, you have to include it as part of the system. Now, this is the way a system evolves if it's isolated and completely not in contact with anything else. We will have to come back to ask how it evolves, what happens when you put it in contact with a measuring apparatus. We'll have to have a model for how measurements take place. But this is the way the system behaves if nobody disturbs it during the course of the evolution from time 0 to time t? Okay, we'll have to come back to that. It's an important question.
Could you summarize the assumptions that you started with?
Oh boy. Yeah, really just two assumptions. Well, maybe three. First is that time evolution takes place by a linear operator called u. And that operator is independent of the state that it's acting on. Okay? With me? Okay. That's the first statement. The next statement is that inner products are conserved with time, and that tells you that u is unitary. Okay. From that, we went over to here and discovered that for the small little incremental change is governed by a Hermitian operator. Okay? So we get to the idea of a Hamiltonian. And then we just rewrote that and said, look, the small little incremental change could be thought of as 1 over epsilon times the time derivative of the state vector. Okay, so this is the Schrodinger equation. How do you solve the problem if there's a long time interval, not a short time interval? You basically solve this equation. And we'll talk about how you solve this equation. We'll do so for lots of examples. But, okay. All right, to go on and explain what this has to do with classical mechanics, or what it has to do with the corresponding concepts in classical mechanics, we need a couple of ideas about how you relate classical ideas to quantum mechanical ideas. We need the idea of what is called the expectation value of an observable. It's a bad name. It's a bad name because the expectation value as defined may have very little to do with what you expect the experiment to give. This doesn't have much to do with quantum mechanics. It's just an issue of probability theory. I think we've talked about this before, but I'll just remind you. If you have a probability distribution which looks like this, then the least likely answer that you could possibly get is right over here. It's also the expectation value. So it's a poorly chosen terminology. The right terminology should, sometimes some fancy people, I won't name Murray Gell-Mann, but some fancy people like to call it the expected value. Well, it's even less the expected value than it is the expectation value. It's the average value. It's the average value, and the average value of something can be a value which the thing can't even take on, a possible value that it couldn't even have, the average value. For example, if you assign heads +1 and tails -1, and you flip the coin, what's the average? 0, but you can't get 0, so it's got nothing to do with the expected value of an experiment. But nevertheless, it's called the expectation value, and we will call it the expectation value. But it's the average value. Let's talk about the average value of a observable given a particular state. All right, so our state is A. I said I was going to change the psi, but sometimes I will, sometimes I won't.
Could we go back to the expectation value for a second?
Yeah.
Maybe I think I just have to clear my head of statistics, but when I look at that picture you draw, I see a frequency distribution.
Yeah.
So to me, the middle is not the average. It really is the expected value. It's the value that's going to occur most frequently.
No, definitely not. This one here, it never occurs. Never, ever, ever. Let's even make it worse.
Okay, what are the x and y values? What are the x and y axes representing? Because I keep seeing
P is the probability, X is some variable, something that you measure. This could be the probability for finding a particle at different locations, okay? All right. It could be that for some particular state, the probability, let's make it symmetric about the origin just to, it could be that the probability distribution looks like this. I meant to make this symmetric, and is really very, very zero in the neighborhood of the origin here. There's no sense in which x equals 0 is expected. You can do the experiment forever and ever and ever, and you will never get x equals 0. You'll either get an x somewhere in here or here. So to call it the expected or the expectation value is sort of a misnomer. It is the average value defining averages in a very particular way. Now, for many, many smooth probability distributions, in particular probability distributions that don't have big holes in them, something like this, let's say, it can very often be the case, and very often is the case, that the average value is the most likely value to get.
So it's statistics, they call it the mode, right? The most likely value. What's the peak?
The peak there is the most likely value. Yes, by definition, the top of the peak is. And in many, many cases, if you have nice, simple probability, Gaussian probability, bell-shaped curves and so forth, then the expectation value or the average value is usually quite close to the average and peak value and so forth. They're all usually close to each other. But certainly there can be violent exceptions. The coin or the spin, which can only be +1 and -1 and never 0, the expectation value and the average value are quite different. Okay, but that's just a little sermon and gave me a chance to badmouth my friend Murray Gell-Mann.
Question, if
yeah.
you take a spin where the apparatus is perpendicular, then probably 50%, but you make it very unlucky, you hit 1 million ups in a row.
Yeah,
The
yeah.
average would be up, but that's not accurate.
Yeah, well, okay. It depends on what you mean by average. There's a notion of average which is strictly mathematical, and we're going to write it down in a minute. There is a unwritten law, which I think it's safe to say nobody really understands, but it's the law of large numbers, that if you do a thing enough times, how many times? I don't know. If you do a thing enough times, you do an experiment enough times, the average gotten by averaging the results of your experiment will be equal to the average defined mathematically to within what? To within the margin of error. What is the margin of error? There's a specific number. Does it really mean that every time you do it, the answer will come out within the margin of error? No. All right, so we're assuming standard probability theory, that if you do a thing, plus this extra little ingredient, this extra physical assumption, I don't even know what to call it, that if you repeat an experiment enough times, the average of your data will be the mathematical average. Can anybody prove that? No. That's a law of large numbers. No. There's nothing you can do to prove it. The reason you can't prove it is because sooner or later, somewheres in the multiverse, somewheres, there's going to be an exception to it. No matter how many times, if you do it a zillion times, a zillion is a number, incidentally. It's not infinity. A zillion is 1 with a logarithm of a zillion zeros after it or something like that. Yeah. Right. If you do an experiment, and there's enough repetitions of it, eventually somewhere, someplace, there's going to be a violation of it. This is closely connected to the second law of thermodynamics. There was a principle. The second law of thermodynamics says that the entropy never decreases. Boltzmann was never able to prove that, and he finally realized that the right law is the entropy probably never decreases, except when it does, which is rarely, except when it does. So I'm not going to try to give you an explanation of why probability theory works. This is to me, very puzzling. But we will assume probability theory works. The statement that it works is the same as the statement that the average of your data will be, for a big enough experiment, will be the mathematical average. All right, so let's talk, well, let's come over to this side here first and just say, supposing we have a collection of, we have a probability distribution for some variable, let's say for lambda, one of the eigenvalues. We're going to measure an eigenvalue of L. Supposing we have a probability for lambda, there it is right there, the thing I called prob of lambda, probability for lambda, and lambda can take on a whole bunch of different values, lambda sub I, let's call them. So this becomes the probability for lambda sub I. Then the average, the definition of the average is the sum over I of lambda I times the probability for lambda I. That's the definition of the average, and we'll represent the average by the symbol, the bracket symbol. Why it's labeled by the bracket symbol we'll come to. Okay, but that's the definition, standard probability theory definition of the average of a quantity. The quantity times the probability that the quantity takes on that particular value, summed over I, and as I said, that's standard definition of average. Okay, what is the average in a state A of the observable lambda? So let's say that A is expanded in a basis. Which basis? The basis of eigenvectors of L. Right? Remember, L is a Hermitian operator. Its eigenvectors form a basis. You can expand vectors in an orthonormal basis. So let's write this in the form alpha sub I, sum over I, lambda sub I. Remember that the lambdas are an orthonormal basis. What is the probability lambda in the state I? Probability for lambda I is equal to alpha star I, alpha I. All right? I maintain, oh, this is the probability, and the average of lambda, let's call it the average of lambda, is the sum over I, lambda sub I, alpha I star alpha I. All I've done is plug in. Let me prove that this is the same thing as taking the vector A, the bra vector A, and sandwiching between the bra vector A and the ket vector A, the operator L. The operator L is the operator whose eigenvalues are lambda. Let's see if we can prove that. It's actually quite easy. All we do is say, let's just plug in, let's come to another blackboard, plug in, and let's see if we can prove that. All right, so let's calculate this creature over here. A is this summation, and let's use also that the bra vector A is the summation over I of lambda sub I alpha star I. All right, so we make a sandwich. The sandwich is the sum over I and J. Why? There are two sums, one for the bra and one for the ket. Lambda sub J, alpha star J. This is the bra vector A, and then we put L there, and then we put the ket vector alpha I, lambda I. Just pure plug-inology. Now, what is L when it acts on lambda sub I? Lambda sub i's are the eigenvectors of L. So when L acts on lambda sub I, we still have sum I, j, lambda j, alpha star j, alpha I, And now L hits lambda I, and it gives us lambda sub I times lambda I. Now all this junk in here is just a number for each I and j. For each I and j, this is just a number. So that means we are called upon to take the inner product of lambda I with lambda j. What is that? Right, it's 1 or 0, depending on whether I equals j or not. Given that, this sum, the double sum, collapses to a single sum in which lambda I and lambda j are identified, and this just becomes sum on I, lambda I, well, okay. Let's cut through some of the steps. If j is not equal to I, you get nothing. If j is equal to I, the inner product is just 1. So this just becomes the sum over I, alpha star I, alpha I, lambda I, which is exactly what we have over here. So we've proved this relationship here, that the average of any observable is just the sandwich, the bracket made out of sandwiching L, the observable, between a bracket, between a bra and a ket. Okay? That's the same bra and ket. The bra and ket associated with the state of the system. Right? That's where this notation of bracket comes from. Okay, that's a good thing to know, that if you want the average of a quantity, just sandwich it between the bracket, the bracket representing the state. Any questions about that? Okay, now I'm going to tell you what we're going to do. What we're going to do is we're going to try to find equations governing the time evolution of these average values. The idea is that under suitable, reasonable circumstances, if the probability distributions are nicely shaped, if they have a sort of nice bell-shaped curve, that by calculating the time evolution of averages, you're doing something pretty close to what classical physics would instruct you to do about calculating the equations of motion of the classical system. The way averages tend to evolve in time, as I said, under suitable circumstances, follows equations which look very, very much like the corresponding classical equations. All right. So our next goal is to try to find the rules for the time evolution of these average values, expectation values. And that's not so hard. We have all the equipment we need to do that. And let's see if we can do it. All right, so at any given time, the average of lambda is given by psi of t, that's the state vector at time t, the operator L representing the observable, times psi of t. In other words, I've just plugged in for A the actual time-dependent state of the system. This is the average of L as a function of time. I don't know, what should we call it? Let's call it, okay, it's the average of L as a function of time. Again, this is a kind of a wrong notation. It's not the average of L of t, it's the average of L as a function of time. We could. We could put the t outside the bracket. That's non-standard. Sub t, but why don't we just go with standard notation? Standard notation, and remember, well, okay, I'm not going to do it. I'm going to just call it average of L as a function of time. Okay, as a function of time. It is a function of time. That's the main thing. It's a function of time. could do something else. We could call it L bar. Another notation for average is to put a bar on top of something. That's another notation for average, standard notation. And we could just call it L bar of t. It means the average as a function of time. Let's do it that way. What would we like to do with this? We'd like to find equations of motion for it. In other words, we'd like to find out how it changes with time by differentiating it with respect to time. I want to take this quantity and differentiate it with respect to time. So let's call it L dot. Now we have bars with dots on top of them. L dot of t is the time derivative of this. Now L of t, that's just some fixed operator. It's some fixed definite operator. All of the time dependence is in the state vectors. The state vectors change with time. The operators, those are fixed. Those are definite operators. So let's see if we can take the time derivative of this here thing. The time derivatives act on the psi of t's. When you take the time derivative of a product, and this can be a product of vectors, it can be a product of numbers, it can be a product of functions, well, functions, the rule is always the same. It's the time derivative of one times the other plus the time derivative of the other times the one. That's very general. So this is going to equal then d psi by dt, the bra vector, L psi, plus psi L d psi dt. Oops, I erased a very important equation, or else I buried it under the blackboard. Let me write it over here. D psi dt is equal to minus I h psi. That's what we're going to stick in over here. So we begin to see that the Hamiltonian is going to tell us something about how average values change with time. The Hamiltonian of classical physics tells us how the corresponding quantities change with time. The Hamiltonian of quantum mechanics will tell us how the averages change with time. All right. We're going to also need the bra version of this. So let's write the bra version of this. The bra version of it is d by dt of the bra vector psi of t is equal plus I psi h. H is Hermitian, and so we don't have to Hermitian conjugate it. It is Hermitian, but we do have to change the sign of I when we go from bras to kets. Okay, so now we're just going to plug in. Let's just plug in, and we'll get L dot, yeah, right, L dot, okay, let's do this one first over here. This one is going to be plus psi, and there's a minus sign from here, minus I psi L h psi. That's what we get from here. How about the other one? The other one is plus I psi h L psi. Or I times the expectation value. We have psi here, we have psi here, I times HL minus LH psi. How about HL minus LH? Is that 0? Why not? HL, who cares which way we order? Well, operators don't necessarily commute. Commute means that you can freely interchange the order of them. In general, this is true of matrices, products of matrices don't necessarily commute. Sometimes they do. And in particular, an operator commutes with itself. L times L minus L times L, that's okay. You can do it there. L times L minus L times L is 0, okay? So is H times H minus H times H. But in general, L times H is not equal to H times L. It may be, but typically not. What is this animal called? H times L minus L times H? It's called the commutator of the two. Okay, so this is a definition given to operators. Well, they could be just H and L. The combination HL minus LH is written with a square bracket, H comma L, and it's called the commutator. Commuting has something to do with passing freely between each other. Exactly what it has to do with taking the subway in New York, I don't know. But it's called the commutator. And so what we have here is the equation that the average of L at any given time, the average of the time derivative of the average is equal to psi commutator HL psi. But this object over here is just the expectation value of commutator of H with L. So we can think of this as an equation relating the time derivative of a certain average to the average of another quantity. I did. Is it plus I? It's plus I. I did. I. Or we can write L dot of T is equal to I, well, average, times average of the commutator, HL, and I'll indicate that by a bar on top of it. So we have equations of motion now for averages in terms of averages. If the probability distributions for everything are nice and peaked, then we really can just say approximately nice and peaked so that the averages are close to the highest point on the curve, and the curve is reasonably narrow so there isn't an enormous amount of uncertainty. Then this basically says that the time derivative of the classical, or the time derivative of the approximate L of T is equal to the approximate average of commutator of H with L. And someone writes, this of course is not quite right, but right anyway, L dot is equal to I times commutator HL. Now, as I said, this has to be taken with a little grain of salt. What it means is an equation among averages. It means an equation among averages, but it's often just written in this form. L dot is equal to H times L. Okay, now, before we finish, I want to remind you of a classical mechanics equation of motion. It's the equations of motion represented in terms of Poisson brackets. Do you remember Poisson brackets? Good old Poisson brackets, fish brackets? Okay. What were the Poisson equations of motion? Anybody remember? And if you, right, d by dt, exactly, d by dt of a classical function, and this could be a classical function of q's and p's. In classical mechanics, we have q's and p's. L, incidentally, is a standard notation for angular momentum. This could be the angular momentum, but right now I'm just using it to represent any observable. d by dt of L is equal to a certain Poisson bracket. And the Poisson bracket is the Poisson bracket of L with the Hamiltonian. Remember that? Probably some of you don't. But I'll advise you to go and look it up. It's in the next to last lecture of the classical mechanics on Poisson brackets. And I will not go through it here. I just wanted to remind you of it. And I want you to notice the similarity. Where is it? Did we erase it? I think I erased it. The similarity of this with dl by dt, average value is I, minus I or plus I lost track. Plus I times the commutator of H with L. Now incidentally, okay, let's just point out one thing. Poisson brackets have the property that if you interchange the two expressions, what happens to the Poisson bracket? It just changes sign. So do commutators. HL minus LH, if you interchange the order of them, change sign. So we can also write this as minus L with H, commutator of L with H. There's a remarkable similarity, and it suggests that we identify the Poisson bracket with minus I times the commutator. Now I've left out a discussion of something. I just realized it just now, and I've completely forgotten about it. What happened to H bar? What happened to H bar? We've been working in units in which H bar is 1. I've been working in units in which H bar, Planck's constant, is 1. The question is, if we were to reinstate Planck's constant and make it not equal to 1, where would it go in these equations? And what's that? Yes, it goes in Schrödinger's equation, that's correct. But how do we trace it? Let's see, how do we trace it? Here's the equation here. I told you that H has the significance of the Hamiltonian, and therefore it has units of energy. So let's look at this equation. The psi cancels out on both sides as far as units go. The units of this psi are the same as the units of this psi. And so the right-hand side of the equation, apart from the psi's, has units of an energy. The left-hand side of the equation has units of inverse time. Inverse time and energy don't have the same units. Inverse time is inverse seconds, and energy is joules or whatever. So we have an equation here which doesn't make good dimensional sense. We need a constant in here, and the constant, we have to put a constant in here. Let's see, where does the constant go? Does it go on the right-hand side or the left-hand side? Where does Planck's constant go? Right-hand side or left-hand side? Either. What?
Either.
Well, if it goes in one place in one thing, then it goes in the inverse in the other place. Okay. So here's all you have to know, is that Planck's constant has units of energy times time. Planck's constant has units of energy times time. So let's see, so energy times time. So we want to put Planck's constant here. Energy times time over time is equal to energy. That's where Planck's constant goes into these equations. And I apologize for having completely forgotten about it, but that's where it goes. And if we follow it through the equations, no doubt it appears over here. I think it appears in the denominator here. Yeah, you see, I got everything right except where I have H, I should have H over H bar. Right? We could rewrite this way, H over H bar. So in all of my equations, wherever we wrote H, the Hamiltonian, we really should have, if we want to keep the units straight, h over Planck's constant, and that goes straight through to here. So really the right equation, including the constants, is the L dt is 1 over h bar here. 1 over Planck's constant. Planck's constant is a small number, so this looks like it's very big. But on the other hand, this is L times h minus h times L. In classical physics, that would be 0. So whatever this is, classically it's 0, and quantum mechanically it must be a small correction to the classical physics, to the extent that quantum mechanics is a small correction to classical physics. And so the commutator is itself something which is typically small and of order h bar. So that allows us then to guess an identification between commutators and Poisson brackets. Now, this is not intuitive at the moment. It's just just looking at two equations and saying, look, if there's going to be any connection between quantum mechanics and classical mechanics, then there must be a connection between the Poisson bracket and the commutator. Namely, Poisson bracket must be equal to minus I over h bar times commutator, or it's usually written the other way. Commutator is I h bar times Poisson bracket. Commutator is a small thing because there's an h bar there. Poisson bracket in classical physics is not a small thing. It's some number. I mean, it's some characteristic quantity which is neither small nor big. And in the same units, the units that you do classical physics, the standard units, meters, seconds, whatever, commutators are very small. That's because they're almost 0. A times b minus b times a is almost 0. Okay. No, I don't think so. I think I. We had a minus I on this side, minus I over h bar, multiply by h bar, and now multiply both sides by I, and use that minus I times plus I is 1. Yeah. Right. It was Dirac who recognized this connection and built his quantum mechanics out of it. He built his quantum mechanics out of making an identification of Poisson brackets with commutators. But of course, the foundations of the subject, quantum mechanics is a consistent subject without having to make any reference to classical physics. The right way to think about things is that quantum mechanics comes before classical mechanics. Commutators before Poisson brackets. You have to derive classical physics as an approximation to quantum mechanics. So here we see some formal similarity. At this point here, we have no idea why this commutator should have features in common with the Poisson bracket. Before we go, let me just say, let me write down some of the features of commutators and Poisson brackets to remind you. And again, all of this should be, at this stage, should be a little mysterious. What is this funny connection between Poisson brackets? But let's pursue it anyway. Okay, let me remind you about Poisson brackets. First of all, if I have two quantities, I'll call them A and B now, or maybe A and B I use for, well, let's just call them L and H. They don't have to be the Hamiltonian and anything special. They're just L and H. All right, the first thing is the Poisson bracket of L with H is equal to minus the Poisson bracket of H with L. Okay? The commutator of L with H is minus the commutator of H with L. So that's a parallelism that we can begin with. Now let's take some other properties of Poisson brackets. there's a lot of properties of Poisson brackets, but let me just write one or two more. If I have two operators, or two, not operators, but two quantities, let's call them L and M. Okay. L times M is itself a classical quantity, and I can compute its Poisson bracket with H. Does anybody remember the answer? I'll remind you, I'll tell you. Go look it up. This is important. It's L, it's the Poisson bracket of L with H times M plus L times the Poisson bracket of M with H. Now in classical physics, the order of multiplication doesn't matter. So you can bring the M on the left or the right, it doesn't matter. You can bring the L on the left or right, it doesn't matter. But this is the relationship for the product of two variables, the Poisson bracket. Go back to the next to the last lecture and check this out. This was one of the properties of Poisson brackets. You can do the same, you can ask the same question over here. Supposing you have Lm and you take its commutator with H, what do you get? All right. This is an exercise. This is an exercise, and all you do is you write that this is equal to LMH minus HLM. And now you start just juggling and adding some terms, subtracting the same terms, and eventually you'll discover that this is the same as this, same relationship, that this is equal to L times the commutator of M with H plus commutator of L with H times M. The way to do this is just write LMH minus HLM and then write out these guys here. This is LMH minus LHM plus LHM minus HLM. 4 terms here. 2 will cancel in pairs, and you'll just get this back. It's a one-step thing. It's a really easy thing. Okay, so you begin to see some pattern that Poisson brackets and commutators must somehow be closely related. The last thing I'm going to show you tonight is about energy conservation. Now, we're not going to consider the most general concept of energy conservation. We're simply going to ask, is the average of the energy conserved with time? We have not even really gotten to what it would mean for energy itself to be conserved in any deeper way. But we can ask, we have all the ingredients now, which will allow us to ask how the average of, here's how our average of any quantity changes with time. No, here it is over here. We can now specifically ask how the average of the energy changes with time. Let's do it. The energy, I claim, is the Hamiltonian, okay? Or its definition, if you like. What is energy? It's Hamiltonian. So let's check and ask whether energy is conserved if energy is the Hamiltonian. This equation would read, the time derivative of the average of the Hamiltonian is equal to minus I over h bar times the commutator of the Hamiltonian with itself. The Hamiltonian with itself, it's h times h minus h times h. H times h is the same as h times h. Quantum mechanics is not that weird. You know, it's weird. But h times h is the same as h times h. So this is 0. Whatever the Hamiltonian is, its average, its expectation value with time is always 0. And so it's conserved in that sense. at minimum in that sense. There's a stronger sense in which it's conserved, and we'll come to it, but even this weaker sense is kind of interesting, and it tells us we're on some kind of right track to be able to compare quantum mechanics and classical mechanics. Okay, I'm going to stop now and take a few questions, and here? Yeah. Probably. I just mean the average. I mean the average defined as summation of probability of lambda times lambda. Okay. So I don't know. What's the standard symbol in statistics for an average in this sense?
Sometimes they write
They do what?
first moment of the distribution mu, they use sometimes.
The first moment of the distribution. Yeah. Okay.
This is lambda.
Yeah. Yeah. Okay. So, I'm used to just calling it lambda. Hmm?
E brackets of lambda.
E bracket of lambda, and that stands for what?
The average of expected value.
Expected value, even though it's not the expected value.
You don't expect to get it.
Yeah. Yeah. Okay. You've never seen the average value with a bar on top of it?
Yeah, but
Yeah.
I mean, it's normal convention is that it means the sample means like you average in things.
Okay. Yeah. When I use the term average, I will mean this. It's also called the expectation value, and I will freely interchange the Dirac notation for the average with the bar notation. Okay. And if that's not standard according to statistics books, too bad.
So over here you wrote down the Schrodinger equation.
Yes.
And then you wrote down how did you go from the left-hand equation to the right-hand equation? Was that complex conjugation or was that Hermitian conjugation?
Hermitian conjugation.
Okay.
Hermitian. But remember that H is Hermitian. We proved that. That was the condition of unitarity, that H is Hermitian.
But how come you interchange the order of psi and H but not DDT and psi?
Where?
On the left side equation, you've got DDT
Here.
psi. DDT is the operator.
This one here?
Yeah.
Yeah. Yeah, the time derivative of a bra vector is a bra vector. The time derivative of a ket... Look, the time derivative is just another way of talking about differences. The difference of two bra vectors is a bra vector. The difference of two ket vectors is a ket vector. Okay? In the limit, the difference becomes the time derivative, or the derivative. So the derivative of a bra vector is a bra vector. The derivative of a ket vector is a ket vector. If you want to take this ket equation, what is the bra that goes with this ket? The bra that's dual to this ket is the time derivative of the corresponding bra vector.
So since time's not an operator, you don't have to worry.
Right. Time is, just think of this as taking the difference of two vectors. Yeah, it's just a difference of two vectors. Right. Exactly. And again, quantum mechanics is weird, but taking the difference of two vectors and replacing it by a derivative when the difference is small, that's perfectly legitimate.
You said that the form of Hamiltonian we will choose depending on symmetry considerations.
Well, yeah.
In the derivation here, we did not put any symmetry consideration so far.
No.
So why is it then that we are getting energy conservation out?
How come we're getting what?
Energy conservation out. How do we know that is corresponding to energy?
Well, we don't know that it's corresponding to energy until we do a lot more. We don't know that we can define it to be energy, the Hamiltonian, but that's not satisfying. We want to see in cases where we understand the classical physics and we understand what energy is, we're going to want to see that the quantum mechanics of the same system, the classical system is an approximation to the quantum mechanical system. Physics is really quantum mechanical. Under certain conditions, such as a system is heavy, basically that it's heavy, that it's big, that it large masses, then the system behaves approximately classically, which means that the average values move in ways which are consistent with the classical equations of motion. We're going to want to see that when we study such big, heavy systems, that the thing that we call the quantum mechanical Hamiltonian is essentially closely connected with the thing that we call the classical Hamiltonian. But we'll come to that. We can't do everything all in one night. At the moment, I'm just showing you similarities, and we're going to want to do better than that. Whether we'll actually get to do better than that, I don't know. We can't do everything, but that's the logic, yeah. Yes.
Getting way back to the electron spin, I think when we left off the last lecture, you were going to show what the probability is to measure something when it's off at it.
Yeah, right. I had saved some time to do that, but I think I've done enough for tonight. Who was it who sent in the solution to it? Yeah, well done. Right, so, but we'll do it, we'll do it. I've run out of steam. Right, we'll come back to that. We're going to come back to that.
So how can your postulates work without a collapse postulate?
What's that?
How can your postulates work without a collapse postulate?
Well, we really want to derive the collapse postulate. But the derivation is deeply connected with something else that we haven't come to yet, and I think we're going to come to it next time, entanglement. The measurement process is really a process of establishing entanglement between a system and an apparatus. And until we've talked about the entanglement process, I think until we do, we simply have to adopt the language of collapse. But next time. Remind me about collapse. I'm close to collapse, so okay.
For more, please visit us at stanford.edu.